everyone. Thank you so much for joining our session. Today we have a very special guest speaker with us. Jing Yu Koh is a PhD student at CMU, and he has done a lot of amazing work in multimodal deep learning and grounded language in vision and language problems. And prior to joining CMU, he was a research engineer and AI resident at Google AI. So thank you so much, Jing, and over to you.
Yeah, thank you, Ahmad. So I'm going to share my screen now and we can start. Cool. Can you all see my screen?
Yes. Yes, we can see yours.
Okay, great. Let me see, how should I? Cool. Yeah, thanks so much, Ahmad, for the invite. And I'm very happy to be here today at the Cohere for AI regional meeting. So I'll be presenting a work that we did recently at CMU with my advisors, Daniel Fried and Ruslan Salakhutdinov. The title of this work is Generating Images with Multimodal Language Models. So we know that large language models have achieved very incredible things. Some of the ones that I'm personally most interested in and the ones that are most relevant for this work include their abilities to learn zero-shot and few-shot from in-context examples, their ability to learn strong text representations, and tap on world knowledge learned from large-scale text pre-training. In this work, we asked whether we can leverage some of these strong abilities of large language models and ground them to pre-train visual encoders and visual decoders. So successfully doing so would allow us to have a multimodal model that can process images and text and produce images and text. Gill is one model towards this approach. Gill, or generating images with large language models, is a multimodal language model that can process image and text inputs. It can generate text, generate images, and retrieve images, and decide when it wants to retrieve images, or generate text. So some of its capabilities include the ability to engage in multimodal dialogue. For example, the image on the left, you can put in an image of ramen noodles and ask a question in text like, how can I make this more nutritious? Gill will respond by generating text such as, you can add vegetables to your ramen noodles, but be careful not to overdo it. And in this case, it also generates an image to accompany the text. So you kind of have an idea of how your ramen noodles will look after you add some vegetables in it. So, Gill is capable of a wider variety of capabilities compared to prior multimodal models. So one of our previous work from Marsh is a retrieval-only multimodal language model. So this model can process images and text. It can generate text, but it can only retrieve images. Gill, on the other hand, can both retrieve images from a database, it can generate novel images, and it can decide when it wants to show retrieved or generated images. In contrast to existing generative models like Stable Diffusion, Gill exhibits much better sensitivity to longer text inputs. It can generate and process dialogue-like text, which models like Stable Diffusion cannot. So one example here is that you can pass in an input like, what about a pencil drawing of one? And models like Gill can understand and resolve this co-referencing and know that one refers to the beaver, which you mentioned previously in the conversation. But models like Stable Diffusion with relatively weaker text encoders can't really handle this as well. So Gill is obviously not the first multimodal language model. There have been a few approaches towards this. The Frozen paper from 2021 was one of the first approaches to ground text-only language models with images. And it was an approach that showed the ability to process image and text inputs and generate text. Flamingo was a scaled-up version of Frozen with new architectural tweaks, and Flamingo exhibits state-of-the-art performance on many multimodal tasks at the time it was released. Blip 2 was also a recent paper that can, again, process images and text, but generate text. So one of our previous approaches from Marsh is one method towards multimodal language models that can also produce images. So from Marsh is a model that can process image and text inputs. It can generate text and it can retrieve images, and it can interleave retrieve images with generated text to produce compelling multimodal dialogue-like outputs. In this work, we extend these previous models. So Gill not only is able of processing images and text, it can also generate text, retrieve images, and generate novel images from scratch. And it decides when it wants to output retrieved images or when it wants to output generated images. Gill is also quite resource efficient, so it requires just 2 A6000 GPUs for 2 days to be trained, because we leverage a lot of pre-trained language models and visual encoders. I should also mention at this point that I'm happy to take questions at any time during the call. So feel free to raise your hand or unmute and ask questions. So Gill leverages several of the compelling abilities of large language models. Gill is able to retrieve images, generate images, and generate text. It uses the abilities of pre-trained text-only language models such as in-context learning, improved sensitivity to input prompts, and their abilities to generate long and coherent dialogue-like text. So these are some abilities that models have learned using large-scale text-only pre-training that we leverage in this work. Gill is also model agnostic. So even though in this work we use a 7 billion parameter large language model, the OPT model, we use the clip encoder and the stable diffusion image generator. All of these components can be swapped out for other pre-trained models, and you might imagine improved performance using stronger models released in the future, or swapping in other types of visual models like OCR models to introduce new capabilities to Gill. So I mentioned earlier that Gill can process image and text inputs, but how exactly do we train it to do this? So Gill is trained with several training objectives. The first one is learning to process interleaved image and text inputs. So I might have one image, one text, one image, one text, and so on. And we need to learn a way of processing these types of inputs so that the model can handle arbitrarily interleaved multimodal data. So given an image and caption example from conceptual captions 3 million, we have one image and a corresponding caption that corresponds to it. So you have a cute image of a cat here, and the corresponding caption is an European short-haired cat in a woven basket. We first pass the image to a visual encoder, which compresses it to a sequence of vectors represented here by the yellow block image. So these are a sequence of vectors that represent the image content. We tokenize the caption using some word tokenizer that the language model uses, and we pass it to the input embeddings of the language model. So both the image sequence and the token sequences are combined to form this sequence length by 4096 dimensional input embeddings. So this is a sequence of continuous vectors that we can pass into the frozen large language model. The model is trained to predict the next token in the caption, and this is done by optimizing the cross-entropy loss. So conditioned on the image vectors and all previously generated tokens, the objective of the model is to predict the next token in the sequence. So given like the image sequence, the first token it will predict is A. Given like image sequence and N, it will predict gray and so on. So this is kind of like standard image captioning training that was done in other similar models like Frozen, Flamingo, and I think also Blip 2. Yeah, so this trains the model to learn to process images, because in order to be able to caption them well, you have to understand and process the correct content in the image embeddings. The second task that we train Gill to do is to learn to produce images. So in this setting, we want to produce images, and how we do this is that we append our image tokens to the caption inputs. So these image tokens are special tokens that we train the language model to learn, that represent image content. So we pass this entire sequence with the special image tokens to a large language model, and it produces a sequence of embeddings from the last hidden layer of the language model. So each of these tokens comes with an associated 4096 dimensional vector that represents something. We also compress the image using the same visual encoder, and it's passed through a linear layer. When we retrieve an image, we take the first image embedding, we pass it to a linear layer, and we run an info NCE loss between these two. So we're learning to map into a space where image and text vectors are semantically similar. So if you have an image of a cat and you have a caption that describes a cat, you might imagine that they are relatively close in this embedding space. So we train this using the info NCE loss, which is the standard way that you train retrieval models like SimClear and Clip. Now for generating images, we take the full sequence of image tokens, the R image tokens. We pass this into a model that we call Gill Mapper, which will be explained in the following slide. And we train this by minimizing the mean square error loss against the stable diffusion text encoder. So we put the same caption, an European short-haired cat in a woven basket, into stable diffusion's text encoder. And we apply the mean square error loss to minimize the difference between Gill Mapper's output and the text encoder output. So if you learn a good mapping, you would be able to directly pass Gill mapper's outputs into the stable diffusion text, the stable diffusion image generator, allowing you to synthesize images from the R image tokens. So what is Gill mapper? Gill mapper is a way for us to produce the sequence embeddings that stable diffusion expects. So given the R image embeddings, we pass it to a transformer encoder. This goes to a transformer decoder that takes as input L learned queries. So this is kind of similar to how the data model does it with object detection. You have L queries where L is the number of embeddings that stable diffusion expects. These go into the transformer decoder, and we predict L by 768 dimensional sequences. And as described earlier, this is trained by minimizing the mean square error loss against stable diffusion text encoder. So what we're doing here is essentially like learning a mapping between our image tokens from the language model and stable diffusion's input space. So this is useful compared to just having linear layers because these like image generation models, as we found, require very dense information. So if you were to use a single image embedding like we did for image text retrieval, it does not work very well. You cannot capture a lot of the information that you require for generating images, which is why we require like more image tokens, a more sophisticated architecture for synthesizing these, and so on. Yeah. So this was kind of like the overview of the Gill architecture. And I want to pause here for a bit in case there are any questions about the model architecture or the training objective before we run through an example of what happens during inference time. Cool. So during inference time, you might have a scenario where you have an image input and you want to ask a question like, how should I display these at the farmer's market? So I have an image of cookies and I want to ask Gill like to give me some suggestions of how to display them. We first encode the image using the visual encoder. So this again compresses it to a sequence of vectors over here represented by the yellow image block. We tokenize the caption and pass it to the language model's input embeddings. So this also becomes a sequence of embeddings. Every subword token in the sequence becomes a number, and we pass it to input embeddings to extract vectors for them. This entire sequence again goes into the language model, and the language model is asked to auto-regressively generate text outputs, token outputs. So it might say something like, I think, blah, 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 and at the end, it produces the special image tokens that we've trained it for. We take these image tokens and we pass it to a linear layer that is trained to either retrieve or generate. So it outputs either 0 or 1. If it outputs 0, we want to retrieve an image. So when it wants to retrieve an image, we have a pool of image candidates from some training database. We compute their similarity score against the output of the image 1 embedding with the trained linear layer. And we take the image with the highest similarity and output that as the retrieved output. When we want to generate images, we take all R image tokens and we pass it to Gill mapper. So Gill mapper produces a sequence of embeddings that is compatible with stable diffusion's text decoder, and it synthesizes an image condition on those embeddings. So in the end, we have either a retrieved image or a generated image corresponding to every sequence of image tokens in the model. And the final output is something like, I think they look best when they're on a tray with a little bit of space between them, followed by the generated image in this case. So we've replaced the image tokens with actual images, and we've kept the text tokens from the model. So this is one example of how Gill might operate when you pass in image text inputs. It generates text, it generates images, and it decides when it wants to produce retrieved or generated images. So that's how Gill works. Yes, there's a question.
What if it does not want to generate an image, like the query is not something that requires to generate an image? What will it do in that case?
Yeah, so if it doesn't produce image tokens, it means that the model will only produce text outputs. So this is kind of like a standard image text to text task. So you might imagine that VQA is something like that. We will only generate text, we won't generate images. So that's also like one of the things that Gill can do. It can generate just text, or it can generate both text and images. So in the event that like no images are generated, it will just output text. Cool. Juan has a question, I think.
Oh yeah, thank you. I was just wondering in the decision model layer, whether when it decides to retrieve or generate, how do you optimize that? Like how is it like training data that goes in, or
Right.
how does it decide
so we
kind of like the loss?
Yeah, right. So we actually like it's omitted on this slide, but we collected a bunch of training data. So you have a caption and you have a generated image and a real image, and you get people to annotate whether the retrieved image or the generated image is better. So we have this like pet data of about 1,000 examples that we use to fine tune this linear model. So yeah, we do have like some data set of that we use for training.
Thank you.
Yep. Cool. Yeah, thanks for the questions. Yes, another question.
Yeah, so here you basically have two branches of the model that's not related to each other than the input. So I just wonder if there's a way to like merge them. Also, like, isn't there a paper somewhere about like how diffusion models are like secretly classified? Like, can you use something like that and say you put some noise in your each candidate, and the one that denoise the best is probably the right image?
Yeah, I think something like this might be possible. The reason is two separate branches is I think we found that the input expected by both models was just too different to, and we found improved generation performance with using more tokens. But yeah, I think something like what you're describing could work. I'm not sure if it's the most direct way to do it. So one advantage of doing it this way is that you don't always have the correct candidate images in your retrieve set. So people might go on your app and ask like, show me a image of a squirrel on a beach drinking a martini. We don't really have like relevant images in the retrieve database because they're all real images. So in that case, if you start from a denoised image, you might not necessarily get as novel of an image as if you were to start from scratch. So I guess in a way like this might be a bit more general and maybe a bit more direct if you're just generating the embeddings. Another reason is that if you generate embeddings, it's a bit more general. So it doesn't always have to be an image generator. You could put in some other image model, like it could be a segmentation model or something. And this approach would probably still work for that. So it doesn't always have to be a diffusion model. It's one of the reasons, I guess.
I guess it's also true that if you try to denoise every candidate image, you will probably take more process.
Yeah, it will take a lot of time, I think. And if you're denoising just the top image, then maybe it's not too different from retrieval. So yeah, I don't know. Cool. Yeah, thanks for all the great questions. Yeah, so this is how Gill works when you provide inference examples. Now the question is like how, so we observed that Gill produces quite nice qualitative outputs. You know, it can generally answer image text questions, it can produce reasonable images. But it's difficult to evaluate this task because there's not a lot of benchmarks that have image text inputs and image text outputs. So we evaluate it by following prior work in using this visual storytelling dataset. So visual storytelling consists of a sequence of text and image inputs. So this usually describes some kind of story that someone is telling. So the inputs might be like, I was on vacation in this nice brick hotel. I took my dog Trixie for a walk, blah, blah, blah. And the task that we describe here is you have to generate the last image corresponding to the fifth story sequence. So after a while, she got tired and had to take a rest. We put this entire sequence into Gill and some baseline models. And it has to decide what the correct image is for the last story sequence. So this not only requires passing the last text input, but it requires processing the previous text inputs and possibly the image inputs to generate good outputs. Because if you look at just the fifth story caption, after a while, she got tired and had to take a rest. If I didn't read any of the story before this, I would probably think that this was describing a human or something. But it actually describes a dog. So when you put this entire story sequence into our model, it's able to condition on the corresponding context, even though it's very long. It's able to condition on image inputs to generate more semantically relevant outputs. So in this case, Stable Diffusion actually generates some kind of like house, hotel-like thing, whereas our model understands that the last caption is referring to the dog here, and it produces the relevant output that is much more similar to the ground truth. So we measure this performance on this task by measuring clip similarity and LPIPs. So the evaluation here is how closely aligned the generated image is with the ground truth image. So the higher the clip similarity, the more relevant a generated image is compared to the ground truth. And we find that when you just have one caption, Stable Diffusion actually outperforms our model slightly. So it's able to produce more relevant images when you have a smaller number of captions. But as you start to increase the number of captions, our model actually outperforms Stable Diffusion. So when you provide 5 captions to both models, our model actually achieves a higher similarity and a lower LPIPs. LPIPs is a distance metric, so lower is better. So when you provide 5 captions, our model actually does better than Stable Diffusion. And interestingly, if you provide all the 5 captions as well as the 4 previous image of the sequence, our model does significantly better, which suggests that it's able to condition on the image content in the previous images and produce stylistically and semantically relevant images. So previous models like Stable Diffusion and other similar generative models can't really condition on images very directly, and they can't really condition on multiple images, multiple captions. So this is kind of an encouraging result because it shows that Gill is able to leverage the abilities of the language model to produce better images conditioned on multimodal inputs. The other evaluation that we conduct is on visual dialogue. So visual dialogue consists of a series of Q&A pairs of dialogue-like text discussing an image. So you might have something like, question, is the man alone? Answer, the man is alone. Is it sunny outside? No, it is not. What color is the snowboard? And so on. So the task that we evaluate here is condition on this entire sequence of dialogue-like text. How well can we generate the image that the dialogue is discussing? So this is a difficult task because it requires conditioning on long dialogue-like text that is very out of distribution with the conceptual captions 3 million image text data that we fine-tune on. And it requires understanding like what they are talking about, because sometimes it's not so direct. You know, it's not just a single image caption that says a white dog next to a brown dog. Usually they are discussing it in more abstract terms or more like indirect terms. So similar to before, we actually find that when you provide less rounds of dialogue to each model, so when you provide just one Q&A pair, Stable Diffusion actually does a bit better than our model. But if you start to provide more question-answer pairs, 5 rounds of dialogue, 10 rounds of dialogue, our model actually does better than Stable Diffusion with the longer dialogue sequences, which shows that it's able to better process longer dialogue-like text, and it benefits from increased context, which is something that prior text-to-image generation models don't really do that well. Yes, question.
Yeah. So I think I find this strange in a good way, if you will, if I understand it correctly, since when you train the Gill mapper, you are minimizing the mean squared error of the output and the output of the stable encoder. The model learn to be somewhat wrong in a good way.
Yeah, so I think maybe what you're saying is, so we also did point this out in the paper that if you think about it, like both models have the same generator. The only difference is the text encoder. So Stable Diffusion has the clip text encoder. Our model has this large language model, but both models use the same image generator. So what this seems to suggest is that we learned like a good mapping between the language model and the generator, so that even with longer sequences, our model can produce relevant embeddings. So it's kind of like interesting because despite both models using the same generator, and despite us essentially like distilling from Stable Diffusion, we still perform better with longer like text. And we kind of attribute this to the abilities of the language model to be more sensitive to input, to be able to do things like co-reference resolution better. And yeah, so this is kind of why we think like it's an interesting but somewhat unexpected result. Yeah, and we do have some like ablations later on that hopefully like disentangle this a bit more. But yeah, that's a great point. Yeah, so one ablation that we did is on the effect of context. So when you provide increasing amount of context to Gill, it does better on the visual storytelling task. So one caption, it gets like similarity of about 58. 5 captions, it gets like a bit over 60. But if you provide just 2 captions by 1 image, it actually does a lot better, which suggests that it's able to condition on image content quite well. So the visual storytelling examples are usually stories of someone's like Flickr photo album. So normally they are taken in the same location or they have the same style. So if someone appears in the first image, they might also appear in the subsequent images. And if the photos were taken in a dark place, usually all the photos are. So this is one reason why like conditioning on images helps to improve the similarity of generated images. So models like Gill, which can process image content, can also condition on this to generate more relevant images over just text. So this experiment shows that multimodal context is worth more than unimodal context in this example, and it allows us to produce more relevant generated outputs. Yes, question.
Hey, sorry, can I ask a question before, just in terms of the language model part? So
yes.
You said the original loss function, you were doing like cross entropy loss versus the caption that the image was given with.
Yes.
And
so it's yeah.
So you're comparing the given caption with the caption that you generate, but you give your caption to it as well.
Yes. So this is during training. During training is done using teacher forcing. So every token is generated assuming you have the ground truth inputs of all the previous tokens. So this is the same way that like typical image captioning models and most language models are trained, with teacher forcing.
Oh, I see. Yeah, okay, that makes sense.
Yeah, because I think like autoregressive will take too long. So this is
right, okay,
standard training. Yeah, thank you. Cool. So yeah, so I think this was interesting. Multimodal context is worth more than unimodal context. Another ablation we run was on the Gill mapper module. So I alluded earlier that we require denser input sequences for image generators. We require like stronger mapping networks compared to just linear mappings. So we ran an ablation experiment where we compared like results against stable diffusion on image quality as well as visual storytelling. So if you instead use a linear layer or an MLP or a simple transformer, it does like significantly worse as measured on clip similarity against visual storytelling. So Gill mapper and the Gill mapper module seems to be essential to having strong performance on producing embeddings for stable diffusion. So without Gill mapper, the generation performance is quite a lot worse. Other abilities of Gill include text to image generation. So because it's using a language model to process the input text, it's able to process longer captions a lot better. It's able to be more sensitive to input prompts and produce like better embeddings. So we actually compared some examples from the party prompts dataset against stable diffusion. So we find that Gill is able to do better on certain examples where the caption is a bit more complex. So a dignified beaver wearing glasses, a vest, and a colorful necktie. He stands next to a tall stack of books in library. Stable diffusion actually doesn't get the beaver by default, but our model is able to kind of handle that. Yeah, I don't really know if it is a beaver, but it's more beaver-like than the one on the left. This example of a drop-top sports car also highlights that our model is able to be more sensitive to these inputs. So stable diffusion misses the car completely, but our model gets the car and the bend in the road. Yeah, and some similar examples. Stable diffusion misses the snowstorm, but our model gets both the penguins and the snowstorm. So some of these examples, as well as the quantitative results, show that our model is able to condition more strongly on input text. Yeah, so I think two questions. Maybe first Ahmad, and then Vatsala.
What version of stable diffusion are you comparing with?
Yeah, so all of these examples, including the one used in our model, is the stable diffusion version 1.5, I think, on Hugging Face. Yeah, so we didn't try with version 2 because I think it's slightly different, so might have some modifications to do, but all the experiments are with V1.5. Yeah, I think there was another question maybe by...
Yeah. So I missed a part of the talk, so sorry if this is redundant, but I wanted to ask, like, what do you think Gill Mapper is doing that helps it get better at conditioning, like better at text-to-image generation than Stable Diffusion?
So I think there's a... So it's not just like Gill Mapper that helps it, but it's... So both models use the same image generator. So the only difference in Stable Diffusion and Gill is the large language model and Gill Mapper. So I think both these things are what helps it do better. The large language model allows you to extract stronger text embeddings than Stable Diffusion has access to. So these embeddings might be more sensitive to context and more sensitive to longer prompts. Gill Mapper is just a way of converting these language embeddings to inputs that are compatible for Stable Diffusion. So there are two things that need to be done for a strong image generation model. You need to have like good language embeddings, and you need to have a good mapping from language embeddings to Stable Diffusion. So either one of these things could be the reason why it's better, but probably the larger language model and the stronger text representations are what are primarily contributing to it being better at these tasks, I think.
I see. Thank you for that.
Yeah, thank you. Cool, yeah, great questions. So Gill is also able to perform some other capabilities. So one of this is image refinement. You can ask Gill something like, I want to paint a landscape with mountains and a river. Can you help me find some inspiration? In this case, it actually generates text that says like, I'm not sure, but it produces an image anyway. So this is, I think it's a good representation of what I wanted to paint. You can follow up by saying, can you show me some with horses? And it's able to condition on this, the previously generated image and the original input text to produce a relevant output. And this is actually quite a nice painting, I think, even though the rivers are kind of gone here. You can again follow up and say like, can I have something more abstract? So even though you don't say, can I have a river and mountain landscape that is more abstract, it's able to again do some form of co-reference resolution and produce abstract outputs. In this case, we've lost the horse, but it's demonstrating some kind of capabilities along these lines. So I think Gill was, oh yes, Ahmad.
So you have this indenting type of dataset in your training data, or is it like an emergent capability? And secondly, like, was it trained in like
yeah
format or yeah?
So we don't have this data. So we only fine tune on conceptual captions, which are image and captions. So this is kind of, you can think of it as emergent in some ways. It's probably because everything is represented in the embedding space of a large language model. So things like compositing concepts, referring to previously seen things. The language model has already learned some of that in pre-training. So as long as we learn a good mapping from image to text space, we can do some of these tasks, but it's not explicitly in our fine-tuning data, if that makes sense.
Yeah, that makes sense. And second was that like these chats are more in instruct format, and I think that the actual conceptual captions is not in the instruct format. So did you perform that conversion
Yes.
to instruct
Yeah,
format?
so we don't have instruction data actually. No, so we didn't do any conversion. All of it is image caption data. Yeah, so I think this is actually one of the I think future work points. So if we had some kind of instruction annotated data, it would be a lot better at producing the correct image outputs or following instructions. But at present, it doesn't. Yeah, so all of these are learned from like caption data, which is also interesting. Yeah, it's possible that like the text pre-training had some kind of instructions, but we don't explicitly fine-tune on that. So I think Gill was an interesting like proof of concept that you could even do something like this, an image text model that produces image and text. There's a lot of future work that can be done. So one of it is we can train on more diverse data. So conceptual captions 3 million has, as the name suggests, about 3 million examples for training. We would probably get a lot more from training on the Lion dataset because this is quite small by modern standards. In this work, we also only train on image caption pairs, and training on interleaved data that is kind of available now on Hugging Face would probably help a lot. This would also allow Gill Mapper to be probably more aligned to Stable Diffusion given more training data. We can also apply this to much larger language models and stronger visual models. So in this work, we use a 7 billion parameter language model, which is the OPD model. But since we've done this, more language models and stronger language models have been released. So it's likely that swapping this out for Llama, Llama 2, and maybe the 13 billion parameter version would allow you to do a lot better on some of these tasks. And lastly, we can probably use like more carefully fine-tuned language models. So those that are instruction fine-tuned or dialogue fine-tuned would probably do a lot better on certain tasks. And one thing here, as maybe I suggested in this example, is that Gill at the moment doesn't have very explicit image conditioning. So all images are represented as a sequence of vectors, 4 vectors in most of these examples. And you lose a lot of image content when you compress images to such short sequences. So finding ways to incorporate more explicit image conditioning, such as having denser sequences or longer image sequences, would probably allow the model to be a lot better at things like image editing, where it can preserve the content of previously generated and input images much more carefully. So the model is available on Hugging Face Spaces. You can try it at this link. All the code, paper details, and implementation details are also available on the website, jyco.com/Gill. I'm also happy to take any remaining questions now, or you can also email me at a later time if you have any questions about this talk. Yes, Ahmad.
So another question that I had, that when you are doing like similarity with for the retrieval images, you said that you have database of
Yes.
So like, does those images need to be trained or fine-tuned in some manner, or like you can add any images, use any images for retrieval?
Oh, okay. You mean like when you like during inference time when you retrieve images? Is that what you mean?
Yes.
Yeah, so in this work, we actually just like retrieve from the conceptual captions training set. But I think in principle, because our visual encoder is Clip's visual encoder, and Clip was trained on like internet scale data, probably anything resembling natural images would work. If you change the distribution too much, it might not work as well. But I think in general, like any like image within a standard deviation of what is considered normal would probably be fine. Yeah, it probably can't retrieve documents and stuff, but images generally should be okay.
So regarding lack of data, this may be a bit too new, but have you looked into multimodal C4?
Yes, I think I've seen that. And also Hugging Face released something last week called ID Fix or something. So is this like interleaved data set? They have text, image, text, image. I think those type of data would be very useful to train such models. So we kind of show that you can bootstrap like interleaved image text capabilities. Like even though we train on just captions, you can process image text data, but it would be a lot better if you train explicitly on interleaved data. So things like multimodal C4 and things like IDFix would help a lot. And yeah, I think it would help a lot, and it would be very useful to explore this in future work.
What do you think are like some of the things that this model lacks, like which are shortcomings, you can say?
Yeah, so I think evidently when you give a talk or when you write a paper, most of the things are what highlights the model's capabilities. But in the paper appendix, we do have a section on limitations. I think one of the key limitations is that at the moment, it's very hard to get the model to naturally produce images. So the question here is like, when do I produce an image? When do I generate a text? And fine-tuning on interleaved data like Chuanchi posted would probably help a lot. So you have some kind of notion of when you should produce images, when you should produce text. In this work, I think one of the major limitations is that Gill doesn't always produce images when it makes sense to do so. You can prompt it with things like, show me an image. And we do like some kind of inference time hyperparameter tuning where we increase the probability of producing images. But it's also not great. So one of the limitations and one thing that would be great to address is finding ways to allow it to more naturally produce images. So this might be instruction fine-tuning, training on interleaved data, things like that would probably help a lot. I think that's like one of the limitations that I think would be great to fix. Yes, Kola?
Yeah, along the same lines, is it the balance between sort of retrieval and generation images? Is that like, yeah, have you found that it's like just like hard hyperparameter to tune, or is that like, does that come out naturally?
Yeah, so we kind of train this on like some data set of labels, right? But it doesn't work that well, I think. So I think the data set that we trained on is from party prompts, which consists of generated images, generated image captions. So the task there is kind of distinguishing between images that you want to generate and images that you want to retrieve. So if the task is something like, I want to retrieve images whenever I want to retrieve a factual image, a real image, then it works well. If the caption is like fantastical, like squirrel drinking a martini, and I want to generate an image for that. If it's something along these lines of like separating generation versus retrieval, I think it would work quite well because that's what our fine-tuning data is on. But if it's something that's a bit more out of distribution, then probably it won't work that well. So I think it depends on the application. And nowadays, like image generation models are really good. So a lot of the things it generates they look real anyway. So I think it depends a lot on like the actual application. But yeah, if it's something similar to this, then it would probably be okay, I think.
Cool, thanks.
Yeah, thank you for the questions. Yeah, I see a comment in the we actually considered this. So yeah, I think one of the things we thought of when doing our demo is that we maybe just show both images and the user decides what they want, which I think is probably the correct way of deploying something like this. But I think the decision problem is also quite interesting from a machine learning perspective. But yeah, Ahmad.
So after like fine tuning and creating this chatbot, does the original LLM capabilities like were they affected in some manner, or
yeah, that's a good
like
question. So we do have some results on VQA that we will update the paper with soon. So on image and text to text, it does as well as similar models. I think what you're asking is like text to text. And actually, in this case, it does exactly the same as the previous model because what we do during training does not affect the language model at all. The whole model is frozen, and the only thing we train are these like image embeddings and these linear layers. So if your input does not consist of images, it's exactly the same as the original language model, down to like the floating point values of the logits and everything. It's exactly the same. So it doesn't affect the original performance. Yeah, and another question that some people ask is like on things like VQA, does your model do worse because it can generate images? And we find that it actually performs comparably or slightly better than similar models trained with the same amount of compute. So being able to generate images doesn't detract from answering things like VQA and image captioning.
I think we don't have any more questions.
Yeah, sounds good. And thank you for the wonderful questions. Again, our code, paper, and model weights are available here, and you can feel free to reach out if you have any other questions.
Thank you so
and
much.
Thanks again, Ahmad, for organizing this. Yeah, thank you, and hope to see you again at some future meetings, I guess.